Well, last time we talked about lipids, and it probably didn't get by you that actually in the book goes in a different order. The book actually talks about carbohydrates first. I like to talk about lipids first. While there is some complexity with those lipids that we just went over, many of them can be looked at as just these chains of carbons. Once again, I'm just going to kind of zigzag now because each one of those points represent a carbon. And then, of course, we could also imagine there'd be these hydrogens coming off of each one of these points as well. So in this respect, this visual of a example of a lipid, this is okay, is pretty simple. I think it's a pretty simple concept. A whole bunch of carbons, kind of in a straight line in this example right now. It's all single bonds here, no double bonds to create a kink. And we saw that these lipids are really good for energy because we could be breaking down these bonds, and because these bonds that hold together, there's energy in here, we're going to break them and release it for energy. So great for energy. But we also saw that the lipids, specifically phospholipids, are the key to our cell membranes and our membrane-bound organelles. So in that respect, they're, important in structure. The structure of the membranes, but structure. And this is going to be a little bit of a repeating theme that we're going to see these four organic molecules being used for often energy and structure, but in different fashions. So now let's go ahead and get to carbohydrates. And another thing I may have already said already, you're often going to see that it's in the word. So right now, I want you to notice the word carbohydrates. What do you think of when you see the word carbo? And what do you think of when you see hydrates here? What words do you think of? Well, I tend to think of carbon when I think of carbo, and when I'm over here, I think of water. Hydrate, I think of water. And what we're going to find out in carbohydrates, for every one atom of carbon, we have the equivalent of one molecule of water. And that actually creates some fascinating aspects to carbohydrates. So let's jump into it. So what are carbohydrates? Well, obviously we find them, I'm sure, once again, this is a biology class for a fitness degree program, that you're going to find your carbohydrates in your whole grains, in your breads, your pastas, your rice, your sweets, your simple sugars, and your fruits and vegetables and so forth. But what are they from a molecular level? Well, first of all, carbohydrates are made up of subunits called monosaccharides. And I mentioned that last week when we talked about the concepts of monomers. This is the smallest form of a carbohydrate. We'll give examples in a couple of slides. And like I already said, carbohydrates are made of the atoms carbon, hydrogen, and oxygen. And the ratio is of 2 to 1 here, 2 to 1 ratio of 2 hydrogens for every 1 oxygen and 1 carbon. So for example, glucose. This is going to be really our most important sugar. This is our blood sugar, our main energy source right here. Glucose is a 6-carbon sugar. It's not the only one, we're going to find out, but it's a 6-carbon sugar. So it falls under the category of hexose, because hex here means 6. Hexose. Versus glycerol. We're going to call glycerol a carbohydrate. Technically, if you remember it from the lipid talk, it doesn't kind of fit in this exact ratio of CN, H2ON, but we tend to group it under carbohydrates. It's pretty close. It has 3 carbon atoms, so it would be called a triose. Of course, tri meaning 3. What do they function? Well, lipids were great at long-term energy. Carbohydrates are great at short-term energy. A little bit for long-term energy storage. Once again, we'll get into that. But really, carbohydrates are great for short-term energy, and lipids are great at long-term energy. And they are found in both simple and complex forms. Now, I do want to make a little note. Do you see up here on the hexose, ose, and the triose, we have the suffix OSE, and that's used to represent carbohydrates, as opposed to ACE, ASE. You've already heard me use the concept of enzymes. We're going to talk more about enzymes with proteins, but basically right now what I need you to know about enzymes is enzymes help chemical reactions go to completion. And really, without these enzymes, for all intents and purposes, the chemical reactions just simply wouldn't happen. So really, enzymes drive the chemical reactions within the cells of our body. Now here's a whole different concept, stereochemistry. Stereochemistry refers to the 3D structure of a molecule. All right? So when you have a larger carbohydrate like a glucose, well, once again, we need to start thinking in 3D. And if you think of it in 3D, well, initially we have this linear form over here on the left. And we have these carbons, and once again, here's our carbons. And we see that we have a carbon 1 here, 2 here, 3, 4, 5, and 6. Well, what will happen is, in 3D space, if you can imagine kind of that branching chain, and we've got these hydroxyls coming off of it, this number 5 carbon will want to actually bond to the number 1 carbon and form a ring. It will want to cyclize, form a circular structure. It's actually energetically beneficial. It prefers this cyclical structure over here on the right, okay, to its linear structure over here. So really, while we often see glucose in this linear form in books, really it would much rather, in reality, be in this circular form. It's more energetically favorable to be in this ring type of structure. And now let's look at this again. We actually have the ring where we have this one extra carbon out here that's outside the ring. Okay? And I should note that once again we have these hydroxyl groups, the OH, and I see an OH here, I see another one over here, and notice that it's below this carbon. I have another OH here, and it's below the carbon. Oh, but wait, on this carbon the OH is above it. And on this carbon over here, the OH is below it. It's the location of these hydroxyl groups that are going to be the primary difference between different carbohydrates with the same carbon number. And in fact, looking at just glucose, we have the linear form of glucose right here, but notice we actually have 2 circular forms of glucose. We actually have what's known as alpha glucose and beta glucose, and the difference is this number 5 carbon, whether it attacks this carbon up here, the number 1 carbon from this side, or this side, really above or below. So depending which way it goes, it actually creates a different form of this ring form of glucose. Look at right here. Notice on the number 1, on the alpha glucose, the hydroxyl group is below, but on the beta glucose, the hydroxyl group is above. And three-dimensionally, this will actually have effects on how these molecules are going to work within the body and within the cells. So going more into stereochemistry, giving the example of fructose versus galactose. What I want you to notice here, over here is galactose, and once again, here's its linear structure here, and over here we have its circular structure. But now over here we have fructose, once again linear, and circular. And if we look, they are both 6-carbon sugars. I'm going to go back to the glucose. 1, 2, 3, 4, 5, 6. Oh, wait a minute. So is glucose. What's the difference? Where are these OHs in relation to their carbons? What about fructose? Oh, wait a minute. Once again, a 6-carbon sugar. I'm going to start up here. 1, 2, 3 is labeled, 4, 5, and 6 is right here. But notice, because of where these hydroxyl groups are, actually even moved over what's known as my carbonyl group here, this C double bonded to an O, it creates a very different three-dimensional structure. Same number of carbons, but very different stereochemistry. And they function very differently in the body. Fructose can be digested in the body and used for energy. It enters what's eventually can actually enter what's called glycolysis. It's the process of breaking down glucose for sugar. It can actually be modified and actually enter glycolysis, how we break down sugar for energy. Galactose cannot enter glycolysis directly. We can't just throw it in there. In fact, it has to be converted to glucose for us to be able to use it. And there we go. Galactose can't be used for energy and must be converted to glucose via enzymes. Hey, those enzymes, those chemical reaction drivers, if you will, to be used for energy. All right, so that's the concept of thinking three-dimensionally. Now let's talk about what are simple carbohydrates. A monosaccharide is a 1-carbon ring, such as, once again, glucose. Here's my glucose ring. Right here. Whereas a disaccharide is the fusion of 2 of those rings, such as maltose, down here, which is a fusion of 2 glucose molecules. All right. Well, that begs the question, how do these disaccharides form? For example, hey, here's on the right both sucrose and lactose. Sucrose being a combination of that glucose, our blood sugar, and then fructose, we've already mentioned, also a 6-carbon sugar, but it creates a 5-ring, right? 5-membered ring, and that's our fruit sugar. And then lactose, this is our milk sugar, which is galactose, the monosaccharide galactose, and glucose coming together. So this is milk sugar. Well, you already know how these things happen. It's through that dehydration reaction again, specifically esterification. So once again, we have those hydroxyl groups that will basically end up losing a water, and we have this bond with this oxygen in the middle. That's why it's called an ester. And so in order to form a disaccharide, we take 2 monosaccharides, we lose the water, we dehydrate it, and we get this bonding in here. Now, once again, if we count up all the carbons, and we count up all the oxygens, and we count up all the hydrogens, really, both of these disaccharides would count up the same. However, you can already see, even though this is not a 3D format right now, you can already imagine, I hope, that these would be very different molecules in 3D space. And their 3D structure is very, very important. Because if we think of sucrose, that's table sugar. And of course we can digest that. We will break it down into glucose and fructose, and we can use it for energy. What about lactose, milk sugar? Well, actually, the vast majority of organisms on this planet that actually are mammals, I should say, the vast majority of mammals on this planet actually stop being able to digest lactose, milk sugar, after weaning from their mother. Humans are a bit different. They can continue, for the most part, for most people, to digest lactose. And why is that? Well, in order to digest lactose, well, we have to be able to, once again, break it down. We need an enzyme. And guess what? That enzyme If this is lactose, the enzyme we need is lactase. Hey, that's not shocking, right? Up here, to break down sucrose, we need an enzyme called sucrase. Well, we always have that. And for humans, most people always have this. However, in some individuals, they develop an inability to develop this enzyme anymore. They stop making this enzyme lactase, so they can no longer break this down. If you have lactase, we break this into glucose and galactose, and we already know we can use glucose, and we also already know we can convert galactose to glucose, and we can digest milk sugar. But if you can't break it down with lactase, well, guess what? There's some bacteria in your small intestine that are just dying to get a hold of some milk sugar, lactose. They can digest it, but you can't. I may have already mentioned in a previous lecture, I think maybe even in week 1, we actually have more bacteria cells in our body than our own cells. They're just small, and oftentimes this bacteria has a bad connotation in our mind, but we actually have good bacteria in our body that helps us digest things. Well, way down in our small intestine, we have bacteria that would just love to get a hold of a whole bunch of milk sugar, lactose. And if you can't digest it because you no longer make lactase, the bacteria will, and they will go to town. And of course, these are the people who we call lactose intolerant, and all of a sudden you get a lot of GI distress, a lot of gas, because the bacteria is having so much fun and eating so much of that lactose. My point with all this is the enzymes to break down these disaccharides are very stereospecific. When I say stereospecific, once again, we think about specificity due to its 3D structure. So even though they're very similar, sucrase cannot digest lactose, just like lactase cannot digest or break down sucrose. Well, we just saw how we could actually create a disaccharide, but what about larger carbohydrates? What about complex carbohydrates? And that goes with the concept of polymerization that we once again already talked about, making large complexes of these subunits of molecules coming together to make much, much, much larger molecules. Poly, of course, meaning many. And what we're trying to form here are macro large molecules, right? So macromolecules can be created via polymerization, okay? Think of a polymer, okay, of those individual subunits we already called monomers. So this hopefully is a little bit of a review from what we already talked about. In carbohydrates, remember, we have all these hydroxyl groups, all these OH groups coming off. And they are all potential sites for esterification. Remember that branching to create those complex carbohydrates. So remember, esterification is that type of dehydration reaction, which automatically should make you think, once again, building. So we can create these big branching networks of carbohydrates. Well, that's what complex carbohydrates are, and there's 3 main categories. The main one for us is glycogen. That's the storage form of carbohydrates in animals. That's what we use. And it tends to be cross-branched with all those hydroxyls like a Christmas tree, and you can see that in this picture on the right over here. And basically what it does is it stores glucose, that sugar that we need, in a metabolically inactive state. Remember, glucose, it's a fuel, right? So think of it like a little gasoline. We don't want to store gasoline. We don't want to store, say, a whole bunch of cans of gasoline in our trunk because it would be unstable, right? Same thing here. We want to store our fuel source in a metabolically inactive state. And whenever we do need it, all we do is we just chop off some glucose off the tree limbs, if you will, of glycogen, and then we use it as blood sugar. Then we also have starch. That's the storage form in plants that tends to be more linear, more non-branched. And another form you're going to find in plants is cellulose, which we can't digest, but termites can. Now, it has a special form of branching I won't get into here. Your book briefly talks about it. But basically, why can't we digest it? Well, once again, because we don't have the enzymes for it, but the termites do. Now, I did mention that we want to store our carbohydrates in a metabolically inactive state. It's once again kind of safely storing our gasoline, if you will. And that form is glycogen. Well, we can store about 1,400 calories of glycogen in our muscle. We are also going to store about 320 calories in our liver. So once again, when we think carbohydrates, we want to think about quick, short-term energy, but it can also be stored for longer-term energy in the form of glycogen in your muscle and in your liver. And that's it for now. Next, we move on to my favorite, proteins.